like a number and say, okay, suddenly we have to turn in what units is values, right? So like 1,000 or 2,000, and then we need to make it go there.
So at the point that then make this go to something.
Yeah, that we can. I guess that we can control it and then work through whatever these things are.
Oh, sure.
Right.
Yeah.
What doesn't happen here is that when it's not close enough, it won't increase the power.
And do we?
Like we're going to only start moving at like 30, but the output now is 10, but it's still like 15 error on.
This is the first iteration.
Oh, the parameters are at 0. Nothing will happen, of course. But we can, of course, set the parameters now. Oh, actually!
Yes! I think it's maybe even, it works.
No, it's not.
Turn it.
Oh, it counteracts my finger. Cool.
Look, it's amazing.
It's amazing.
The efficiency.
I can't move it anymore because, yeah.
I'll be attempting to manual tune this PID system. The DT is set at 10 milliseconds, and I'm going to switch between target values of 256 and 768 to test this property. We're going to start by having the I and the D parameters set at 0, and we're going to try to find the p-value, the lowest p-value for which a stable oscillation occurs. So I'm going to turn on the motor, and right now this was a p of 0.65, so we have to set it a bit higher. Let's try 0.7. So here we can see that there's a stable oscillation. Maybe I can make it a bit lower. 0.68. Still oscillating stably. 0.66. It's getting slower. So probably will be 0.67. So by the manual tuning rule that we got from Wikipedia, we should set this to about half of that. So I will set for the manual tuning the P at 0.35, which I did just now. Now we want to increase our Ki until some offset is corrected. So let's start with 0.05. And actually we see there's an oscillation occurring, so I'm going to set this a bit lower still, 0.02. There we go. Error of 5, which is quite good, but as we could see, it takes quite long to get there. It's going immediately to the value with a value of D of 3, and the error is around 1, actually. Almost no error. Here we got error of 0. So these parameters actually seem to be quite good. So we ended up having a p-value of 0.35, I of 0.01, and D of 3. These are the PID values that this came up with. Yeah. Alright, now I'm going to perform Ziegler-Nichols tuning of the system. So I'll be starting with a p-value where I'm pretty sure I'll get a low stable oscillation. Let's try 0.6 as a p-value. This seems to be too low. Let's try 0.8. There's a period here, but I think we can get it a bit lower. So let's try p of 0.7. That's a fairly low value. Let's choose this as our KU. So from the screen I can read off values for the period around, for one of the swings, around 17. So we double that, that will be 34 for a period. Again, we're not dividing by, we're not multiplying by the dt, because we also don't have that in our PID formula. So we will set our p-value to 0.6 times Ku, according to the Wikipedia formula that we're using, which is 0.6 times 0.7 is 0.42. This is what we end up with. Error of minus 24, not very good. For I, we use 1.2 times Ku divided by Tu. Tu being the period of 34 is 1.2 times 0.7 divided by 34 is 0.025, which is also not very good. Now we still lack the d value, which is 3 times Ku times Tu divided by 40, which is 1.785. So d of 1.785 leaves us with this. So this is our Ziegler-Nichols tuned result. I would say it's not that bad. The error is quite low, minus 4, 0, minus 19, that's alright, 31, minus 18, 31, 8. So yeah, value is quite low. Let's say the manual tuning is still much better, but the Ziegler-Nichols approach could be used for us, in this case, as a nice starting point for a manual tuning method, to get an idea of what sort of values we want to use.
If the potentiometer misbehaves, it will be turned off.